So we will work on some word problems today from our textbook. And then, so I think for the first 1.5 hours, we'll do problems from the textbook. And then I will jump back to problems from my old test. We have very, very little parts not done yet. But at the end of today, you should be able to do all problems from my old test one. Okay. Let's see this number 36 from 5.2. From 5.2, section 5.2, number 36. We have done some problems already or something similar to problems in 5.2 before. A National Ambulatory Medical Care Survey administered by Centers for Disease Control found that the probability that a randomly selected patient visited doctor for blood pressure check, so let me use BP check, is 0.593. The probability a randomly selected patient visited doctor for urinalysis, probability for urinalysis is 0.064. Now the question is, can we compute the probability of randomly selecting a patient who visited the doctor for blood pressure or urinalysis by adding these probabilities? Can we just add them, basically? Probability of BP check, or union, urinalysis, according to what we know, the inclusion-exclusion formula, this is probability of BP check plus probability of urinalysis minus probability of the intersection. Okay, BP check, intersect urinalysis. That's what we know in general, right? Now, the question is, can we just ignore this one? Can we just ignore that? Can we just add these two and ignore that part? Depends on what we know about doing BP check and urinalysis. Are they disjoint? In other words, so this question boils down to, are events BP check and urinalysis disjoint? Are these two events events that cannot happen at the same time? Like when somebody goes see a doctor, if that person does BP check, then for sure that person will not do urinalysis. If that person you doing urinalysis, is that for sure that person will not do BP check. Okay. If they are disjoint, if so, which is not true, if so, then the probability of the intersection will be 0, right? And of course, then probability of the union, this becomes 0, right? Okay, then you can just add the probability. Okay, if they are disjoint. Okay, but what we know is not. Okay, what we know is not. But we know the blood pressure check and urinalysis not disjoint. Okay, such that it's not equals to 0. Therefore, we can't just add them. However, we know one thing for sure. Okay, we know one thing for sure. If I continue with this computation on the in the black color here, this is equals to 0.593 plus 0.064. It will subtract by some number, right? We will subtract by some number. With that, we know that the probability of somebody, a patient went for BP, blood pressure check or urinalysis must be less than the sum of these two numbers. Okay, must be less than the sum of that two numbers, so 0.657. It is not 0.657, okay? It is not. But we know it must be less than that because we know that these two events, BP check and urinalysis, are not disjoint. Therefore, this is not an empty set. Therefore, the probability will not be 0. The probability of the union later on will be 0.657 minus some positive number, right? Therefore, it must be less than 0.657. Okay, so going back to the question, can we compute the probability of blood pressure check or urinalysis by adding these probabilities? The answer is no. Why not? Because those two events are not disjoint. Therefore, the probability of the intersection is not 0. And therefore, the formula will be the sum of those two numbers minus some non-zero number. Okay, so if we look back, I'm basically saying this. Under what situation? So note, maybe I go back and make it normal view. Note, when can we use this formula? Probability of A union B equals to probability of A plus probability of B only. Okay, we know in general the formula is probability of A plus probability of B minus probability of the intersection, right? So when can we use this guy only without this? Without this. That is when A intersection B is empty set. Okay, therefore the probability of that intersection is 0. Okay, I kind of mark it wrong. Okay, when the probability, if those two events are disjoint, then the intersection will be empty set, the probability will be 0, then consequently, the probability of the union is equals to probability of the sum of those probabilities. Okay, so let me rewrite that. I will say it this way. I will say it this way. So that's the general formula. General formula. The inclusion exclusion formula, right? Now, but when those two events are disjoint, then probability of the union equals the probability of A plus probability of B minus 0, right? Okay, probability of the intersection is 0. Okay, that's when you can just omit the last intersection, the probability of the intersection. Let's go on. Number 38. Getting to work. According to the US Census Bureau, let me enlarge that. According to the US Census Bureau, the probability of that a randomly selected worker primarily drive a car to work is 0.867. Probability drive a car is 0.867. Probability that a randomly selected worker primarily takes public transportation to work is, so the public transportation is 0.048. Now, then our question is, are these two events, driving themselves or using public transportation, are disjoint? Can you find somebody who drives to work at the same time use public transportation to work? I don't think so. If that person drives, then that person don't need to use public transportation, right? If that person use public transportation, of course, that it means that person don't drive, right? Okay, so from there we conclude, of course, I'm thinking, right, with the event of driving and the event of using public transport are disjoint. I think the only time somebody, of course, this is just a very, very wild guess. Okay, the only time somebody drive to work and use public transportation at the same time, if that person actually drive the bus home, let's say, and then the next morning that person use that bus, and just like this person is a bus driver, let's say, right? Okay, and that person drive the bus home, and then tomorrow morning that person actually start driving from home and just start the work right away. But I don't think that's the case, right? I don't think we have that case. I mean, even if you are a bus driver and then at night when you are done with your work, you still bring the bus back home. No, not back home, back to the pool, right? The bus pool. Okay. Now, then that's why in part A, they can ask that question. What is the probability that a randomly selected worker primarily drives a car or takes public transportation to work? So, probability driving or public transport. Then this is equals to probability driving plus probability public transport. Let me write the third term. Minus probability of the intersection, drive and public transport. Okay, but we know that will be 0, right? So this is 0.867 plus 0.048 minus 0. Okay, then I will use my calculator. I get 0.915. Okay. By the way, I think this may be true for area like LA, that most people when they go to work, when we go to work, most of the time we actually drive, right? Okay, and we have less than 5%. That's what I know. I mean, it may be true, or the number is very close to what we have in LA. Okay, that the proportion of people primarily use public transport to work is less than 5%. Okay, but as far as I know, in Manhattan, New York, okay, most people actually use public transport. Okay, the number is the other way around. From here, we actually say, I'm not trying to criticize LA government. Okay, no, I'm not trying to criticize LA government. What I'm trying to say that in New York, the phenomena is actually the other way around. Most people use public transport. Okay, the reason is when the space is very small there, I heard, and expensive, such that if you drive to work, you pay a lot more for your parking. Okay, you pay a lot more for your parking. On the other hand, why LA don't have a good infrastructure for public transport? I was told one of the big reason is because, well, of course, some policies also, right? I'm not here, again, I'm not here to criticize, but one of the reason is that we are in the earthquake, we are in a part of Ring of Fire, okay, Pacific Ring of Fire. Okay, so we have a lot of earthquake here. Therefore, having underground train, for example, is risky or quite expensive. It's not like Manhattan. It's on very, very solid geology. How to say that? The ground is a hard rock. Okay, the ground that we have in LA, I was told that it's not as solid. It's not strong enough such that when they need to enforce that, it will cost a lot more. Okay, I agree that our bus system here, our MTA, are not really that good also. Okay, and not very well established. Okay, but again, I mean, we were the one who chose our public official, right? So we don't blame the government only. It's like, hey, when we chose those people, we chose people who don't have a focus on public transport. It is also possible because we have our own attitude. I mean, I myself, like if I use public transport, it's not really convenient for me. Okay, but I want to say that I really look forward to a situation where public transport becomes something convenient for a lot of people and easily available. Okay. Now, of course, I don't want to push people to use public transportation by purposely increasing the parking fee, like what happened in New York. That's like people use public transport there not because they want to, but because the choice of driving by car is more expensive. Okay. But I am for public transport, even though I myself drive my own car. Okay, but that's because of convenience though. Okay, for my convenience. Well, so look into that when they don't we become a public official. Okay, especially the elected one. Okay. Part B, what is the probability that a randomly selected worker neither drive a car nor takes public transportation to work? So probability of not driving by car and at the same time not using public transport. Let's take a look on the Venn diagram. This one is a bit harder to explain without Venn diagram. So let's look at this. So use driving alone. and then public transport. And they are disjoint, right? We say they are disjoint. Now, the thing is, we are looking for something not in driving. So not yellow and also not blue. Outside of yellow and outside of blue at the same time. So which part will that be? That will be the part outside of those two circles, right? Is that right? Okay, so this is actually equal to probability of outside of either those two, either one of those two, outside of driving or public transport. But that's equals to 1 minus probability of driving or public transport, which is 1 minus 0.915. Now that 0.915, I got it from here in part A. Okay. And that will be 0.085. Neither drive a car nor takes public transport. Maybe the one doing the carpool, or maybe by bicycle, or just walking. By the way, however strange you heard that, okay, one of my favorite professor at KCLA actually walked to school. Yeah, he actually walked to school. He lived like a couple block from KCLA, and then he was like middle age at that time, but quite conservative in sense like, oh, you know what, I need to exercise anyway, so every time I go to school, I walk, you know. He's still very healthy though, so he really get benefit from living nearby, and he saved. The funny thing is like he saved his gas money, and his insurance is so low. He told me that after driving his car for like 3 years, the mileage is not even 1,000 miles. It's like 3 years, not even 1,000 miles. You know. And I was like, why do you need to buy the car? Well, Thomas, I still need to have a car if I need to buy grocery, right? And I said, but you live nearby grocery store anyway. I said, well, if I buy a lot of stuff, I cannot just push the cart home. Yeah, that's him. You know, he's quite a funny guy. Part C. What is the probability that a randomly selected worker does not drive a car to work? So probability of not driving car to work. That's 1 minus probability driving a car to work. This one is easy. That's 1 minus 0.867. That's 0.133. Can the probability that a randomly selected worker walks to work equals to 0.15? Part D. Probability of walking be 0.15. Is it possible? Is it possible? Well, we have computed probability of not driving and not using public transport is 0.85, 0.085. Okay, and this number is already less than 15%. Remember I said that it's either walking or bicycle, right? Okay, either walking or bicycle or carpooling is only at most 0.085. Okay, so probability of walking to work must be less than that, right? Must be less than that. Okay, notice that walk is the event. Walk is the event outside of driving, not outside of driving, and outside of public transportation. Okay. As if part of that is walking, right? If the total area here, the one in purple, is only 0.85, right? If the one I color in purple is only 0.085, then the walk part must be less than that, not more than that, right? Okay, so that's a good question with some logic. Okay. Is it possible when somebody say, oh, you know what, we have 15% of our population actually walking to work, and then you use this number to say, no, somebody's lying here. Okay, maybe this 15% is true, but it means one of the earlier information, driving to work or using public transportation, are incorrect. Okay, so that's how we see the reasoning behind it. Okay, that's for 5.2. This is the harder question though. Seems like not a good idea to use this problem as a warm-up, but we did 5.2 before. Okay, we already used that inclusion-exclusion formula, which our textbooks call a general addition formula. Okay, let's see 5.3. 5.3, we will do some exercise here. Okay, but I will start first with the following statement, the following background. Definition: events A and B are disjoint or also known as mutually exclusive if these events can't happen at the same time, can happen or can occur simultaneously. And we denote that by A intersection B is empty set. Okay. We use this notation earlier, and I actually gave you the Venn diagram, what it looks like. Right? Now, event A and B are disjoint if they cannot happen at the same time. Let's say this is event A and that's event B. They don't have any overlap. Okay, that's what we did earlier in 5.2 for the case of driving to work by car and using public transportation. They are mutually exclusive. They are disjoint. Now, in this section, we have another terminology that some people confuse them. That's why I want to recall that definition of disjoint earlier. Okay, events A and B are independent if the occurrence of event A does not influence or basically does not increase or decrease influence the occurrence of event B, vice versa. Okay, knowing event A happens or not doesn't tell me anything more or less about what will happen to event B. Okay, and that's the meaning of independent in true sense. Okay, in true sense, even in our daily life, when I say I am independent of you, okay, let's say I date somebody and then we broke up, right? And then I said, well, once we broke up, of course, then we're supposed to be independent, right? Okay, now, but when I say I am independent from that person, it means what? It means my decision is not influenced in any way with that person's decision. Okay, let's say she's want to go to a party. Will that make me don't want to go to that party? Okay, if I say I'm independent, then doesn't matter. I know that she goes to that party or not. Okay, it doesn't matter. Or the fact that I go or I don't go does not depend on my knowledge of she goes to that party or not. Okay, it's not disjoint. It's not disjoint. Like some people like to say this, oh, you know what, I'm independent of that person, so if I know that person goes there, I will not go there. That's not independent. That's disjoint. That's mutually exclusive. Okay, it sounds like independent, but you basically say, if I know that person goes there, I will not go to that place. In other words, my decision is based on what that person does. That's not independent. That's mutually exclusive. Okay. By the way, I heard that a lot though. I heard that a lot from my friends back in Indonesia, especially when we were in undergraduate study, right? Some of my friends, they were dating and then they broke up. Okay. And then they say, oh, well, we are now independent. Okay, sounds good. Okay. And then when I ask both of them come for, let's say, study group, they say, oh, that person is there. I won't be there. I thought you say you're independent. Okay. Well, I'm independent. That's why I don't want to be there because that person's there. Well, that's not independent. That's mutually exclusive. You and I study statistics together. We know what it means. Okay. Yeah. Independent means your decision does not depend on the other event. Okay. In our daily life, for example, these two are independent event. Okay. Like I toss a coin. And roll a die. Okay. Do I need to tell you what I get when I toss a coin for you to decide the probability for you to get, let's say, a 3 when you roll a die? Let's say I get a head. Okay. Let's say I get a head right now. Does the probability of getting a 3 change? No. Why? Because we know the outcome of tossing a coin, the probability that you get a head, is independent from the probability you get a 3. Okay. By the way, the notation that usually used in higher statistics, we can use that here. Denoted A perpendicular to B. That's the notation. Okay. In other words, we know, using this example here, the event of getting head is independent of the event of getting a 3 when you roll a die. You cannot say, well, I cannot tell you what is the probability of 3 until you tell me what you get when you toss a coin. Doesn't matter what I get. Okay, when you toss a coin, it's head, what's the probability to get a 3? What if you don't get a head? What's the probability of you getting a 3? Will that be the same? If probability of getting 3, knowing head or not knowing head are the same, then it means doesn't matter, you know it's head or not, it will be the same, right? It will be, they're just independent. Okay, now then what if two events are independent? If A is independent of B, that also means B is independent of A, then the probability of those two events happen at the same time is equal to the probability of A times probability of B. You just multiply them. Okay, so going back to this example, then what is the probability you get a head when you toss a coin, and at the same time you get a 3 when you roll a die, presuming both of them fair coin and fair die? Then that's equals to probability of getting a head multiplied by probability of getting a 3. Probability of getting a head in a fair coin is 1/2. Probability of getting a 3 in a fair die is 1/6. So that's 1/12. Okay, so the probability of intersection is equal to the probability of the product of probability. Now, the consequent to addition formula or inclusive exclusive formula is that, you know, the general formula is probability of A union B equals to probability of A plus probability of B minus probability of the intersection, right? That's the general formula. Now, if A is independent from B, then the probability of the union will be equals to probability of A plus probability of B minus, then we basically change this, minus probability of A times probability of B. Okay, I think I should use the word consequence instead of consequent. Oh, okay, let's start working on problems. Suppose events E and F are independent. So A independent of B. I'm sorry, E and F are. Suppose event E is independent of event F. Probability of event E is 0.7. Probability of event F is 0.9. What is the probability of D intersection? Probability of E intersect F is probability of event E times probability of event F. That is 0.7 times 0.9. That's 0.63. Okay. That's the probability of the intersection. Now, for fun. So, what is probability of the union? What is the probability you get either even E or even F? Then we use that exclusion formula. Probability of the union equals to the sum of the probability minus the probability of the intersection. Okay, that will be 0.7 plus 0.9 minus 0.63, which we already pre-computed earlier. We get 0.97. Okay, they don't ask that, but we can answer that already. Now, number 12. What is the probability of obtaining 4 ones in a row when rolling a fair 6-sided die? Probability of getting a 1 when you roll a fair 6-sided die is 1/6. Now, the thing is, we know that getting a 1 in the first row is independent from getting a 1 in the next row. Right? In other words, we get a 1 right now doesn't change the probability of we get a 1 again. It will still be just 1/6. Therefore, then what is the probability to get 1 4 times? Probability of 1 4 times, back to back. That will be, yes?
So it's the formula that we would use in that question that you have in the quiz about 4 cards being spades. Would this be applicable to it?
That's if you allow repetition. That's if the card that you pull out, you put it back and you can select that again. Okay. The case that we have last time was without repetition, which means the probability of getting a spade again is different from the probability of getting a spade the first time.
Right, because the numbers would change.
Yeah, but if you are allowed to choose the card that you selected earlier, then it becomes independent. Okay. In other words, that's actually a point that I want to mention later on, but good that you remember that. Then yes, that's the difference. When we select cards, or it doesn't have to be cards, maybe marbles, maybe markers, maybe balls, okay, any items, okay. If we allow replacement, we do with replacement, do the selection with replacement. In other words, selected item may be selected again. You basically put it back and up for selection again, then it becomes, the procedure becomes, instead of using the word it, let me say the procedure become independent. Okay, so that's why when you look at your quiz 2-3, don't forget you have a quiz due this weekend. Okay, that quiz 2-3, somebody already emailed me and asked me, Thomas, is it with or without replacement? And I didn't, of course, I didn't answer that question directly, but I say that it has to be different. right? If
You
see.
specify there's one deck, so that answers
Yeah,
that.
yeah. Actually, no, it's not because of one deck. It's because of we say that it has to be with different cards. Let me check. Let me make sure that I actually say that in the question. But yes, that's actually an issue though. Okay, that's actually an issue. So let me see. It's quiz 234, right?
2-4.
Yeah, yeah, from 234. Yeah, quiz 234. Okay, so let me share. Is it? Yeah. So the issue was with question number 4 and number 5. Number 4 CD. Number 4 CD. Suppose 3 different elements. Because it's different means whatever you already selected, you don't put it back. Because if you put it back, you may end up selecting it again, right? Okay. Now, if you may end up selecting it again, if you put it back, then the condition of that box earlier is the same to the condition of that box right now. So the probability will be the same. But no, that's not what we are doing. Okay, why? It's different. The keywords is with the different elements. Okay, now number 5, also the same. In randomly selecting 4 different cards, we are not allowed to select the same cards. Now, this implicitly means that the procedure is done without replacement. Does it make sense right now?
Yes, I'm
right?
following.
So that's actually a key question though. Actually, when that student asked me, so it's actually a student from another class for my East LA College class. Okay, I really didn't want to answer that because that person is actually asking for a very big hint. But at least I know that person actually trying to do her homework early, right? Instead of waiting until last minute. So I say like the keyword is with the different, okay? Because it's different, then you won't get the same card again. Okay. And that person say, "Oh, I see." That it's just like oh, that's the hint is actually there. But the thing is like I understand when this is the first time you do the problems, that the word different may not be significant to you until you realize, oh, that actually means something really big without replacement. Okay.
Yes.
So sure. So I basically already tell you that for that number 4 CD and number 5, it is without replacement. Okay. Now the thing is this though, the same conclusion will be it will still be without replacement, even if I only say 4 cards. Even if I only say 4 cards. Why? I really want to go over to talk about that more because of the following. Notice that when I say the procedure of selecting 4 cards, select 4 cards, it's actually different from selecting 1 card 4 times.
Right. Because the second implies you're putting it back, right?
That's right. This, the second instruction here, then we have issue, is it with replacement or without replacement? Okay. After you select one, the first card, do you put it back? Because you select for 1 card 4 times. Now, when we select 4 cards, I may just grab 4 cards right away at once. You see what I mean? Instead of doing it one by one, select the cards one by one, I can just grab all 4 right away. So you see, like selecting 4 cards may be done by selecting 1 card 4 times, but it may also be done by just grabbing all 4 cards. Okay, now selecting 1 card 4 times, okay, means you need to do it one by one. Okay, this can be done one by one. But
the probability would be
don't
different.
Don't need to. Now this one must be done one by one.
Professor, is that the same as the book notes as acceptance sampling?
Repeat again.
Is that the same as acceptance sampling noted in the book?
I don't really remember which part is that.
It's kind of like when they show you how to subtract each sample individually and then minus it from 1.
What section is that?
Let's see.
Yeah. Please tell me which one is that. Is it from 5.2?
Yeah, I think it's 5 I have it on my computer, but if I minimize my screen, I'm gonna lose you guys. It's where it's right after the, let me see. They're talking about the defective rate of excluding, let me see, excluding shipments. That was like one of the questions. Say, how would you determine the probability of rejecting a shipment?
Oh, I think that one has something to do with complement. Yeah, it has something to do with complement effect.
But it kind of seems it's right after the conditional probability, but it kind of seems like it's the same. You can use that same procedure in order to get the same outcome.
The idea is actually very similar, but even in that case, I believe we still need to look deeper if are they independent or not. Are they independent or not? I will get into that because I'm actually a big fan of that. They call that acceptance probability, but it's part of quality control actually. Let me see. I somehow think, that it will be in my number 20 in this 5.3. Let me show you. Yeah, so that will be number 20 in our 5.2.
Okay. I guess I just wanted to see if they're like if you use, because it seems like you use a similar.
Yes, that's true. So you will see the similarity is actually we keep on multiplying the probabilities.
Mm-hmm.
Okay. Now the thing is, are we keep on multiplying the same probability or different probability? Then it depends on are they independent or not, or to be more precise, do we assume they're independent or not? Okay, let's get to that later on. Let's get to that later on. It's actually one of the questions I will go over. Okay, but I actually here it's number 20. That's the next question we will do. Yeah, that's the next question we will do.
Okay.
Yeah, but that's a good one though. That's a good one because if I change the situation a little bit, then the way we compute it will be different. Okay. Mm-hmm. Let me go back here. What happened to my son? Actually, no, that's my daughter. Okay, number 15. Number 15. The ELISA is a test to determine whether the HIV antibody is present. The test is 99.5% effective, which means the test will come back negative if the HIV antibody is not present. Maybe I write it down. Probability of being negative given the HIV not present is I don't like this notation. That's the correct notation, but let me just simplify that. That's 0.995. The probability that the test coming back positive when the antibody is not present shows positive while you actually don't have it is 0.005. Okay, how do they get that? It's basically when you add this up, it's equals to 1, right? Right. Suppose I don't have that antibody, right? Will my test show negative? The probability is this. Will my test show positive? It will be this. Now then, suppose that the ELISA is given to 5 randomly selected people. Okay, of so many people, you give it to 5 people, randomly select 5 people. So part A, what is the probability of all negative for these 5 people? Okay, so imagine that you have a pool of a lot of people, like 10,000, 1 million people, such that every time you pull somebody from there, the probability that person being negative is 0.995. I don't really like that terminology, saying that somebody is negative, but start the pandemic, that's actually a nice thing. When I send out email to my friends, I keep on saying stay negative. No, I mean, in the past, I usually say stay positive, right? Like live positively, have that positive spirit, right? But then I purposely changed that to stay negative in that sense. Stay negative, please. Stay negative. What is the probability that all of them negative? So probably the first person is tested negative is 0.995. The second person also negative, also 0.995. So on and so forth. So to the power of 5. Okay, that's to the power of 5. 0.995 to the power of 5. Give me a second. So yeah, probability that all of them tested negative, basically you take, you do it one by one, but the probability for each one of them is 0.995. So you multiply that to each other 5 times, okay? So 0.995 to the power of 5. Now part A, probability that at least one positive, at least one of these 5 tested positive will be equal to, when we say at least one positive, that's the same to say not all negative, right? Not all negative. Does it make sense? A probability that at least one, maybe 2, maybe 3, maybe 4, maybe all 5 are positive, right? Basically, we know not all of them negative. But to say not all negative is the same to say the complement of all negative. The complement of that event. That's 1 minus probability all negative. That's 1 minus 0.97525. 0.02475. Okay. Now, let me change the question a bit. So I will still work on number that similar to that question earlier. Let me move it down. I wonder if I can. So I will still work on number 15, but I modified the question a little bit. Okay, I modified the question a little bit. I will say this way. Let me use another color. Okay, modify. Okay, now suppose you have a group of people, let's say a group of 1,000 people. All of them don't have antibody. All of them don't have antibody. However, out of these 1,000 people, 5 of them tested positive, 995 of them tested negative. Okay, let's say we have this group of people. Now, then you select 5 people from here. You select 5 people from here. What is the probability if we select 5? Not from that 1 million people or 100,000 people, right? This is like a limited number of people of 1,000 people. What is the probability that all of them negative? Now we select 5 different people, right? Okay, so the probability, the first one is negative, is 995 over 1,000 times the probability the second person still tested negative is 994 out of 999. You see the difference? The difference with what we have earlier. The case that we have earlier, okay, we don't know how many people there. We just know the percentage of people tested negative. Okay, we don't know how many people there. Now, once we know how many people there, okay, let's say we set up like 995 of them tested negative, 5 of them tested positive, and we need to select 5 people. And we need to select 5 people, then that will be the first one, 995 over 1,000. The second one, 994 out of 999. The third one is 993 over 998, so on and so forth. What happened again? I'm so sorry. Basically, this is what we compute. Now, you will see the following phenomenon. If you select that from a very, very big group of people, the number we get by computing it this way and by computing it this way will be actually very close. Yeah, okay. You know what? I get really disturbed with my children. Let me do part B and then I take a break. Okay. Yeah. Let me do part B and then I take a break. For the first one, you compute that. Part B, then what is the probability of at least one positive? That's equals to probability of not all negative. 1 minus probability all negative, which we compute earlier in part A. That we get from there. Okay, so the difference from the one I do earlier, okay, that's if we don't know how many people we start with. Okay, they just say there's a 0.995 out of so many people, we believe, right? Now that's different from if we know how many people there and we select from that group only. Okay, now number 20, I believe, is a very, very similar question. Let me ask you to think about it. At the same time, I try to talk to my son again. Okay. Suppose that a company select 2 people to work independently, inspecting 2x4 timbers, doesn't matter, just like doing certain work. And their job is to identify low quality timbers. Now, the probability that an inspector does not identify a low quality timber is 0.2. So let's use that not identify. That's 0.20. Now then, part A, what is the probability both don't identify? Notice that they work independently, right? Okay, so the probability that the first person not identifying it does not increase nor decrease the probability the second inspector to identify it. Okay, So this is equal to probability of the first person not identified times the probability that the second person not identified. Okay, now part B is actually a bit harder. How many inspectors should be hired to keep the probability of not identifying low quality timbers to be below 1%? So how many people? So probability all not identify is less than 1%. The question is then, how many people? How many inspectors needed? Okay, if the probability that both of them, two, not identifying will be 0.2 times 0.2, basically 0.2 squared, right? That is 0.04. Right? The probability that both inspectors will not identify that is 0.04. Now, suppose you have n inspector. Suppose for part B, there are n inspectors. Then the probability that all not identified will be 0.2 times 0.2 times 0.2 n times, right, to the power of n. Now we want to keep this to be less than 0.1, 0.01, I'm sorry. Now then can you solve for n? And you can do so by just trial and error, at least for now, right? You do trial and error. I'm sorry, this is not right. I want to give more space. Give me a second. This one going back here. So what is the n such that 0.2 to the n is less than 0.01? Now we know 0.2 squared is 0.04, right? How about 0.2 cubed? 0.2 cubed will be 0.08. I'm sorry, 0.08, which is already less than 0.01. Okay, so we will need 3 inspectors. Okay, that's for quality control. Before I go on to number 26, let me explain this question in different contexts, but the idea is actually exactly the same, exactly the same, exactly the same, exactly the same. I use this example. Okay, it's actually one of the question, I think question number 2 in your upcoming quiz that you need to turn in this weekend. Okay, the case of alarm. Okay, the case of alarm. Okay, for example, the probability that an alarm went off correctly is 0.2. I'm sorry, incorrectly. It's not working right, 0.2. Now then, suppose we have three alarms or three alarms. Right now we call that alarms, huh? But back in Indonesia, we call that waker. Like to wake you up. Does it make sense? So Indonesian words, we adopt English, but we do not adopt that in the way an English speaker use that. Okay, we call that waker. Okay, so suppose we have three wakers instead. Okay, or three alarms. Now, what is the probability that all of them does not go correctly? All of them incorrect. Because they work independently, supposed to be, right? So that would be 0.2 to the power of 3. That's 0.008. Okay. Now, of course, for you to wake up on time, all you need is actually one of them work correctly. You don't need all three to work correctly. Okay, you just need one of them to work correctly. Okay, so probability at least one works correctly that's equals to 1 minus probability all incorrect. Right? So the probability that you will wake up on time is when at least one of them work correctly. And this is your probability to wake up on time. That's why using 3 alarms will increase your chance to wake up on time better, even if each one of them has a pretty high failure, like 20%. Okay, 20% chance of not working well. That also explains how our network being done. I believe that's how I explained it in my video, my lecture video. Suppose that a connection has 20% failure rate. Okay, so let's say from the server to a PC, this connection here has probability of 0.2 to fail. Like just doesn't work for a reason we don't know. Okay, maybe the router is a bad router. It works only 80% of the time. And how to improve the connection? How to improve the connection? Do we buy a new router? The answer is no. That's actually one way, but that's not the only way. And it turns out that may not be the best way. Okay, that may not be the best way. Another way to do that is this. You can use the same router. Maybe that's an old technology. Okay, but still you can improve that so high. The reliability becomes so high by doing the following. Okay, so you use the same type of router, but you build another connection. And you build another connection. Okay, so this is 0.2 to fail. This is to fail. And 0.2% probability, 0.2 probability to fail. So 20% chance to fail. Now, the thing is, the connection between me and my server will be okay as long as at least one of them work, right? At least one of them work. So probability to be connected is equals to probability at least one work. Now, the probability that at least one work is equal to 1 minus probability all fail, which is equals to 1 minus probability of all fail is 0.2 to the power of 3. See, if you only use one connection, the probability that it works is only 80%, right? It's only 80%. It's 20% chance to fail. So 80% chance to be okay, right? Now, but if you use this kind of configuration, okay, the only time you lost connection if all three of them fail. Now, as long as all three of them work independently, then the probability that all of them fail is 0.008. That's the probability all of them fail. So the probability that you are still connected, you have at least one connection working is 0.992. So you see your reliability suddenly increased that high by doing so. What I want to say is this, though. What I want to say is this. Those internet company, how do they improve the reliability of their internet connection? Spectrum, for example. Spectrum. The one that I get a lot of complaint recently in my area because most people use Spectrum here. Okay, most people use Spectrum here. But since we have this lockdown last year, then all of a sudden, a lot of people use internet, especially in the morning, okay, from home, and all of a sudden the reliability gets lower. Why? Because from their server, let's say, to my home server, in the past, maybe they have only one cable. Okay, now they build more. Do they have new technology? No, they don't have new technology. They don't have new technology. All they need to do is actually build more. So if anything here doesn't work, you still have other way, other route to connect with the server. That's actually how they do it. They don't use a new technology. Okay, all of a sudden, it seems like they have a much higher reliability. Okay. If they want to improve this one line here with new technology, okay, you may say, oh, they may use very old router. But the thing is, even if you have newer router, newer technology, okay, the reliability may not be improved that much higher anyway. You know, okay. How about you build a new one? At the same time, you wait until you have new technology. If you have new technology, then you can fix this one, change it to the newer one with higher reliability, and also add this one here, right? Or add another one here. Then at that time, your reliability will be even higher. But before that time comes, just build more connection, and that's how you improve your reliability. Okay. You know that our cell phone connection, our wireless phone is a lot better right now compared to around 20 years ago. The reason is because we have more tower. So Thomas living here, let's say, right? Now 20 years ago, there's only one tower, cell phone tower in my neighbor maybe, okay? And if like too many people make a call at the same time using that tower, of course, then I will get busy connection, not because the other side is not available, but simply because the connection is poor. But once they build more tower, and you can actually look around your area though. Every 1 mile, as I know, in LA, have at least one tower, which they usually conceal. It looks like a tree, but actually when you look further, no, it's actually tower. It's a cell phone tower. Okay, so they are actually connected to each other, okay, and connect to me at the same time. Okay, now of course, and then my phone will choose the closest tower to work with. Okay, but once this not doing well, then my phone will try to connect to the next tower right away, and try to connect with the next tower right away. Okay, so when I connect with this tower, my connection with other tower is in position of standby. In case this is drop, it connects this way right away, and you will not feel any different when you talk to a person. So the reliability becomes much higher. That also explains one more thing. Why they do not want you to turn on your cell phone when you are about to, the airplane about to take off or about to land. Because what? Your plane is here, okay? Because the distance is far and there are a lot of towers underneath, and this plane is actually move really fast, right? So if you turn on your cell phone will try to connect with all these towers at the same time. Maybe you are taking 100 towers at once, and you just need like 10 people doing so and make all this tower down. Okay, right now, of course, the tower is actually working much better. Okay, but you still don't want that though. You still don't want that. Okay, to tell you more, the main reason they don't want that to happen because your pilot in the control room using the same system. If so many passengers doing that, it is possible the pilot trying to connect with the airport, right? And cannot go in, cannot connect it because all the spots already used by the passenger. So imagine that everybody make a phone call, including the pilot using the phone from the plane, and it turns out that the pilot cannot connect. So I need to land, but the control tower cannot connect with me, and I don't know where to land, how to land, which direction, so on and so forth. Okay, and yes, then the pilot will get pissed off and tell you, hey, turn off your phone. Okay, because you make the call, I cannot make the call. Okay, yeah, that's why, because you're too high, then it will try to connect to the closest one, but then there are so many closest one. Like not close, but the closest one, the distance from you to this tower when you are very, very high is basically the same to each one of these. And you basically take all the spots such that your pilot cannot connect with the control tower. So yeah, you stay in the air, right? Okay, so if you like to, I'm not suggesting it though, but if you like flying and stay in the air for a long time, you don't want to land, just make that phone call. Yeah, I believe somebody will come to you and talk to you though. Okay, but that's actually the idea behind it. Okay, so you see the question that we have from here, number 20, is quality control about timber. All of a sudden, I changed the question using the same idea, exactly the same number, exactly the same idea, okay, to teach us how to set up our alarms. Okay, and then I use the same idea, exactly the same idea, to show you how our networking is being done. You see? Okay, now I really want to share with you how I do the one at my home, though. How I do the connection from my router to my Wi-Fi such that, especially because everybody's home, right? So there was one time that everybody's home. I have my mother-in-law watching Chinese drama, my father-in-law watching Indonesian drama, and my sister watching Korean drama, and my wife is actually watching some video from Facebook. Okay, not to say that my son watching Netflix. Okay, and Thomas need to teach. Okay, with this many people using the Wi-Fi or internet connection at once, and all of them video streaming, I risk my router to be overwhelmed. So, and it happens last year, like around March. Last year around March, then I realized, you know what, this gets a lot less reliable on Friday and Saturday. Okay, so then I changed my system. I actually redo it myself. Right now, it's so reliable. Right now, it's never down. And that's because I use different router. Instead of using one router at home, I use two different routers. But my internet connection from Spectrum, only one. Okay, so from Spectrum, okay, I built two connections to two different routers. Like two different, one of them, my old router, the other one is the used one, another router, okay? And then each of this router connected to all of us. So once one of them fail, it can go the other way, like that. Not to say that I have a baby camera at home also. I have baby camera, like last year around this time, my daughter still only a couple months. So I have my family back in Indonesia wants to see her, many, like including my parents. So I set it up that way, such that I have a baby camera that my parents back in Indonesia can see what we do at home. Okay, so that's even more. It takes a lot more bandwidth, and I modified it that way. Okay. With that said, let me ask you to think about question number 26 together with my break. I will give myself 10-minute break and then 10 minutes for you to do that problem. So I will come back at 5:55. At 5:55, you are done with this question number 26. Okay, that's also your break though. Either you do that first and then take your break, or you take your break first and then come back in 10 minutes and then do this number 26. Okay, see you later. Probability among 21 to 25 years old, 29% says they have driven under influence of alcohol. So probability of driving under influence at that age range is 0.29. Now suppose 3 of people in this age range are selected at random. Find the probability that all 3 have driven while under influence of alcohol. So the first person, 29%, the second person, 29%, the third person also 29%. That is the probability that all 3, yeah, so you randomly select 3 and all 3 have that the DOI history. Then that will be 0.02439. It comes from 0.29 being Q. Part B, what is the probability at least one of these 3 has not? So at least one not. That's the same to say probability that not all. Like not all of them, not all 3 have that history of driving under influence of alcohol. That's 1 minus 0.02439. That is 0.97561. Part C. What is the probability that none of these three has driving under influence of alcohol? The probability that one of them, like if you select one at random, the probability that person don't drive under DUI is 1 minus 0.29. That's 0.71. So the probability that none of them, all these three, has that history means the probability that all three has no such history. That's 0.357911. Probability that at least one has DUI. That's the same to the probability that not known. At least one have that DUI history, right? Not known. So that's 1 minus probability of none of them has DUI history. That's 1 minus 0.357911. 0.642089. We will actually do more of this later in chapter 6. This has something to do with binomial distribution. That's why I tend to attack the type of question where we have without replacement. This is the one where we have independent case. Okay, but this is how we do it. Okay, this is how we do it. Number 30. Last one before we attack problems from my old test. Suppose your financial advisor recommends 3 stocks to you. He claims that the likelihood that the first stock will increase in value at least 10% within the next year is 0.7. Probability, okay, the first increase by at least 10% in value if in the next year is 0.7. The likelihood that the second stock increase by at least 10% in the next year is 0.55. And the third one, the third stock increase by at least 10% in the next 1 year is 0.2. The question is, will it be unusual for all 3 stocks increase at least 10% if assuming they actually independent? Okay. Now, to know if it is usual or unusual, we look for the probability, and the probability should be less than 5%. Then if the probability is less than 5%, then this event is unusual. Okay, now let's compute the probability. Probability that all 3 increase by at least 3%, 10% in the next year, because they're independent, right, will be the probability the first one increased by 10% times probability the second one increased by 10% times the probability that the third one increased by 10%. That will be 0.077. That's 7% something, which is more than 5%, right? So this event, so it is not unusual for all three stocks to increase by 10% in the next year. Okay. To be honest with you, plenty of my friends from USC, at least 4 of them asked me, Thomas, do you want to join buying stocks? For some strange reason, even though I study financial math, I have never have a good luck. I have to admit that has something to do with luck also. I never have a good luck with stocks. So I say, no, I'm not. Okay. So instead of I joined with them to buy stocks, I let them borrow my money. I said, you know what, regardless how stocks actually performing, okay, I lend you my money, okay, and then at what kind of interest rate? Of course, because this is not, this is person to person, then my purpose is I don't want to report tax on that, okay? Yeah, call me immoral, doesn't matter, okay? But the way I see is if you can avoid tax, why do you want to pay for it? Okay, so it's person to person. So I actually charged them, I charged them around 10% per month. And they took it. And they say, Thomas, we still make money. Because since the pandemic, the stock markets already went down so badly. And right now it's so bad such that the only way it can go is actually getting better. That's the way we all see right now. Okay, it can only go better. Of course, some company will suddenly bankrupt. Okay, but if you know how to vary your stocks and create your own reasonable mutual funds, like collection of stocks, then you may be able to benefit from this. Now, of course, I don't expect a student can invest right now, okay? Because the way I see it is like if you're a student, you have less chance to work. Even if you work, very less likely you work as a full-time. And even if you work as full-time, then it will not be a lot of you doing that. Okay, like when I was a student, that's the case too. That's why I kind of think that it should not be too far different from my situation at the time. So don't worry, you may miss this chance, but I'm just sharing with you that with statistics, you can do so much in computing the probability, and people see this as a chance. Okay, of course, if you are not well trained, then you cannot quantify this probability. You cannot quantify that, right? You cannot quantify that. With me and my friends, however, we were trained to be able to quantify that. Of course, all of these are approximation, okay? For example, but then we can quantify that in a way that even if any one of them fail to have at least increased by at least 10%, we can play with the configuration in a way that it's still safe and they still make money. Of course, from me, they make less money. Yeah, but so they borrow my money, right? And then they invest in stocks, for example, right? With a larger share, then they can actually control the proportion of their mutual fund better. Okay, but I myself say no. I don't know why I don't really have luck with stocks. Maybe because I focus more into teaching, such that I don't really have time to really look into it. But of course, it's already how to say that it's already an agreement. Like people believe that we cannot go any worse but better, and it will be for any type of stocks, including international stocks, because it happens to everyone. Okay, it happens to everyone. Thomas, do you think it has something to do with China things? The way I see is this: if you really want to look deep into a particular stock, of course, more things to say, but in general, everybody agree that regardless what happened to American Chinese relationship, doesn't matter. Okay, both Chinese stocks, Indonesian stocks, American stocks, European stocks, okay, Asian stocks has a very high likelihood to increase with the availability of vaccine, especially if you, I don't know if you're aware or not, that we already have 4 major vaccines around the world. Okay, and Indonesia has their own vaccine also being developed, and they found out that it's a lot safer. Oh, I'm so proud of them. You know, a lot safer, and the effectiveness is nearly 100%. Nearly 100%, the effectiveness. But the way they did the vaccine is not. It's different type of vaccine. So it's not being mass produced, it's more being personalized. So basically they took plasma from your body, and then they took plasma from your body. So let's say this is the person. Let's say this is Thomas. The way Pfizer, Moderna, including Sinovac, the vaccine from China, they already create the vaccine that comes from the virus that already weakened, or the fragments of the virus, and then they inject that to me, okay, and let my immune system develop to fight that virus, which already being weakened, okay. Now, the problem is we know early in this pandemic that the virus strangely attacks certain peoples with certain blood type more. I think if you are type A, you are prone to have symptoms compared to if you are type O. In other words, the virus react differently depends on the blood type you have. Of course, also if you have some comorbidity, like some other problems with your health, like if you have high blood pressure, diabetes, then you are more likely to have more severe symptoms. Okay. Now that's the vaccine, the major vaccine we have. Indonesian vaccine was developed differently, and the former health minister was actually involved in this Indonesian vaccine. The way they do it is this: they took some plasma, basically my body fluid, they took it out, okay? Then, so this is my blood plasma, and then they introduce the weakened virus there. Now, let this plasma develop its own immune to weaken the virus. Okay, so what happens if the virus is still winning? Then you add more plasma, Okay, basically you use your own body plasma, my own body plasma, to weaken the virus. Now, once the virus is weakened, then I have more antibody here. Then once the antibody already developed, then they inject that back to my body. Now, the good thing with this method is there won't be any rejection. Like, you know, like if you have new stuff coming into your body, it is possible that your body reject that, right? Like, for example, if you have, what is the word? Heart transplant, liver transplant, for example. If you transplant introduce a new things to your body may reject that, right? Okay, now with this method, then the risk of rejection is nearly zero. So far, they tried that to thousands of people. None of them have side effect. And the best part is the immunity level they get is nearly 100%. They don't want to say 100%, but so far they don't have anybody being done with this method actually contract COVID-19 so far. Like thousands of people. They already did that on 1,000 people. Okay, now the thing is for them to incubate these takes some time. Okay, it takes some time. Now, if you are younger, then your plasma tend to be stronger, then it could be only 1 or 2 days, then they already can re-inject that back to your body. Okay, but if your immune system is weak, then they need to modify that a little bit. They may look for your, let's say my dad, for example, right? My dad, his immune system already weak, okay? But his blood type and my brother's blood type are the same. Okay, so they took his plasma and my brother's plasma. In the lab, they see if there's any rejection among these two. If they have no rejection, so basically my dad's blood type or body fluid is similar to my brother's body fluid. Okay, so they mix them. Okay, and then introduce the weakened virus and then inject that back to my dad. Like that. So they already do this kind of modification. Of course, it takes a long time. But what they need right now is they train people in the lab to do this kind of thing. And it's already available at least in 5 big cities in Indonesia. So at the same time, they get more volunteers to apply this. And they also get more nurses and university students, especially those in biological science, to actually do work on this in the lab. You know, which I think it's actually a good thing. Now I'm telling you this because no, it's not because of it is Indonesia. Then I want to say that no, it's actually a technique that I myself didn't think of. Yeah, you may have heard what they call convalescence plasma. It is being used by American Red Cross. So basically somebody who already had COVID, but then survived and recover, they already have the antibody in their blood, right? So they take this person's plasma and then inject that to somebody who is still fighting COVID. But of course, I was told that the blood type has to be the same. Okay? But the thing is, even though the blood type is the same, there is still a risk of rejection. I mean, it's more than just blood type in your blood, right? Okay, now it is also possible that person is way too weak, such that even with a new antibody, the COVID already take over a lot of part of the lung, let's say. So it still fail. Okay, now what would happen here is basically the modification of this convalescence plasma method. So instead of injecting it directly, they actually put it in the lab first. Now, instead of from somebody who already recovered, they use your own plasma, okay, as long as you are still healthy, okay, and then basically do that kind of work, okay. Now, I was told that it is actually, the result is a lot better, but slower. That's the weakness, it's slower. Now, people ask me, so Thomas, what do you think about this vaccine, right? I don't know if I shared this with you before. You will see that I talk a lot about this virus here because in my undergrad study, my final research, when I wrote my thesis, it's on epidemic spread. So I did work with epidemic before, okay, mathematical modeling for epidemic spread. Okay, so for that to happen, I need to learn this at undergraduate level, of course, not that much, right? But still, then when I follow this, oh, you know what? We can do it this way. We can do it this way. Okay, now that's for our 5.2 and 5.3 exercise. Let's do some more questions from my old test. Okay, I think I have a couple more questions I would like to go over with you from my old test. I forget which test did I go over last time. Let me check my notes. Let me check my notes. Last time I did, give me a second. Fall 18, yeah, fall 18 test 1. Let me check. Fall 18 test 1. So at that time, we have one of the questions we had was this one. Let me screenshot for you. We have this at that time. Let me enlarge that. And I asked you to add all of them, right? Okay, now if you don't mind, please do that first. You may want to copy this on your paper and then do that, and then add them. So complete that table. Now, the couple questions that I didn't do yet, like 2 questions I didn't do yet from that test is these questions.
This is probability with contingency, is that correct?
With replacement, without replacement. Probability with contingency table. Yeah, but the case that we are dealing with here is actually multiple event, compound event case. Okay. Let me add this first. So this is 37, this is 45, this is 58. When I add them, 95, 140. Oh yeah, that's right. So this is not 150, this is 140. The one here is 49, 48, 43. Now then, the questions part F and G, we did A to E already. If you look at your notes, or at least my notes from Monday, you saw that I already did part A to E. Now then, that's when we took only one participant. Now suppose if 2 participants, so not one participant selected twice, it's 2 participants, so they have to be different implicitly. If 2 participants are randomly selected from that group, find the probability of selecting 2 participants without associate degree. So how many people there without associate degree? Like the highest education level is not associate degree. The highest education level not associate degree are the one with high school only or the one with bachelor. Okay, so there are 49 plus 43, which is 92. So the probability somebody without an associate degree, maybe no. So that's the number of people without associate degree, or the highest education, the final education level is not associate degree. Now, what is the probability that both, you select 2 people, right? What is the probability of selecting 2 participants without associate degree? Both without associate. Then what is the probability? The first one without associate degree, that's 92 over 140, right? For the first one. Now then, after you get that person without associate degree, what is the probability the next person that you select also without associate degree? Then how many people without associate degree left in that pool? There should be 91, right? Over 139. 92 times 91 divided by the product of 140 times 139. I get 0.430215. To 5 decimal places, that's the probability. How about part B? At least one never smoke. At least one never smoke. The probability at least one never smoke at least one never smoke is the complement of none of them never smoke. The complement of none never smoke. Which is 1 minus probability that none of them never smoke. What is the probability that none of them never smoke? Okay, what is the probability the first person you took ever smoke? Not never, but already smoked before in the past, has the history of smoking. Okay, probability of not never smoke. If you pick one person, the number of people, I should say, the number of people that is not never smoke is 45 plus 58. That's 103. Okay, so the probability of getting a person, the first person never smoke is 103 over 140. The probability that the second person not never smoke is 102 over 139. Let's take a look deeper here. The possible outcomes.
Professor, can't
Yes.
you just say 37 over 140 and then do 36 over 140 as well?
No. If you do it that way, then you will get the probability that both of them never smoke.
Oh, okay.
Right? Both of them never smoke. Okay. What we have here is at least one never smoke.
Okay, got it. Okay.
Right? Okay.
Okay.
Yeah. So if we take a look, the possible outcomes of this is like none of them never smoke. One of them never smoke, because we have all the two people, right? Or both of them never smoke. Now, what you told me to do earlier refers to only one event, this event. While what I want is actually this event and this event. You see? So the way I attack that problem is I compute probability of this, the one in green, and subtract that from 1.
Okay. Yep.
That's how I get the blue and yellow instead of the yellow one only. Okay. Now we can experiment. Let me compute this first. Okay. let me compute this first. This 103 times 102 divided by the product of 140 and 139. I get 0.539876. So 8. That's the answer for this one, right? Now, notice that this number 0.539 actually refers to this number here is the probability of both of these events. Agreed? Now, to show that your answer is only give me the yellow one way to do it is to show that the probability of what you did will be less than 0.59, less than this number. So probability of both never smoke will be 37 over 140 times 36 over 139. That's 0.06845. Okay, so this is for the yellow case only. Okay, so what is the probability? This is a follow-up question. If you dare enough to think about this, you can understand this. Of course, you need to think a bit more, okay, a bit harder, but you can do it. Then how do we compute the probability that only one, exactly one of these two never smoke? Exactly one of them never smoke. I can do it this way, 0.53988, right? That's the probability at least one, okay? Minus the probability that two of them, both of them, never smoke. I get 0.47143. That's the probability one never smoke. But this is only the one method though. Let me show you another method. How do we compute that of these two people, the probability that only one, exactly one of them never smoke? The second method, which I think makes more sense, okay? The probability that one of them never smoke is this, probability that the first one never, and the second person ever, plus, you see the order never and then ever, plus probability that the first person ever smoke and the second person never smoke. This will give us exactly one person never smoke. Okay, so either the first person never and the second person did smoke, plus the probability the first person did smoke but the second person never. You will see when I compute it this way, I will get the same number in method one. Okay, the probability the first person never smoke is 337 over 140 times the second person smoked before, 103 over 139, plus the probability the first person ever smoked times the second person never smoked. 139. Now when I compute, I get 0.195836, but multiply by 2, because both terms are the same actually, right? If you take a look, this guy and this guy are exactly the same numbers, right? That's why I multiply by 2 there. When I multiply by 2, hey, why is it different? Well, I get different answer. I get different answer. Supposed to be the same. Yeah, let me write this down first, and then I check my other numbers in case I have miscomputation. So let me check my number again. 103 times 102 divided by that. Ah, I'm sorry. Totally wrong. Okay, sorry. I make miscomputation here. This is supposed to be 1 minus. In other words, this number that I get here is coming from here. It's coming from here. Okay, so if I subtract that from 1, that will be 0.46012. Okay, now let me change this one. That was a wrong number earlier, right? So this is 0.46012 minus that number. I get 0.391673. I have some rounding earlier. Let me put 3 here. But the different number I get, it's really because of rounding error. 8448. Okay. So yes, that's supposed to be. But I make miscomputation earlier. I forgot to subtract that one. Now the thing is, the method that I did here, the method that I did here to compute this, one never smoked, the first method and the second method, is basically not doable if I need to compute, if I need to select 3 people instead. Then that will be, the case will be a lot harder. Okay, the case will be a lot harder. Let's try that question. Let's try that question. Suppose I change the question now. Okay, instead of 2 participants, I deal with, let's say, 4 participants. Okay, change the question, but instead of two, make it 4. 4 participants randomly selected from that group. Find the probability of selecting 4 participants without associate degree or without associate degree. Now, how many people without associate degree? We compute earlier, there are 92 people without associate degree. Okay, now what is the probability that all 4 of these without associate degree? 92 over 140 times 91 over 139 times 90 over 138 times 89 over 137. Like you need to do it 4 times, right? Okay, and you compute it yourself. Now, what is the probability at least one never smoke? Probability at least one. At least one never smoke. That's the complement of known never smoke. That's the complement of known never smoke. That's 1 minus probability that none of them never smoke. Means all of them ever smoke. All of them ever smoke. There are 100, how many? Yeah, there are 103 people ever smoke, right? So if you need 4 of them ever smoke, it will be done this way. Okay, so that would be 1 minus some number equals to what number? That's the technique. Okay, with this said, then you can do all the problems in my old test one already. If I were you, I will go from the most recent one, if you have that available. Okay, the most recent one, if you have that available. If not, you know what? Yes. Let me suggest you to do this. This weekend, I will suggest you to do, try that fall 18 math 227 test 1. And then, you know what? Let me post that in the discussion board instead. Okay. Let me post that on the discussion board instead. It's our discussion board. Give me a second. Where's our discussion board? Okay, here. So I will post that in our discussion board. Not this one. Oh, I didn't do the discussion board for today yet. I did. This is from last time. Should be up to lesson 6. My bad. This one up to lesson 6. This is the one last time. Don't worry about this. The one today is the one up to lesson 7. Let me fix this. The one today is the one for up to lesson 7. Yeah, that's right. Then let me post the old test here. Previous one. The one we did was from fall 7. Is it? Yeah, fall 18. I'm sorry. From fall 18. Fall 18. And then what else? Let me look back into our last notes. Fall 18, spring 19. I think I only gave you 2 last time. Spring 19, math 227, test 1. Is there any else? Let me check again. Yeah, only those two. Okay, I have these two. Would you like from fall spring 20 or maybe fall 19? Fall 19, let me see if I have fall 19. It could be just the same test though, I'm not sure. Because sometimes I just copy paste my tests. I just stick it with it. And then spring 20. So I give you 4 old tests to work with. 2 of them already done in class. Now, the way I see, you try to work on the one that I already go over. And then after you are good with those, then try to do problems that I have never gone over. Okay?
Professor, the test one is going to go through chapter 5, correct?
Up to, we can say up to this point, up to what I teach today.
Okay, up to 5.
You can say up to 5.3, but it's actually going a little bit to 5.4. Implicitly, the way we did the compound event, is basically has something to do with 5.4.
Okay.
Okay, but let me check this one first. So spring 19, that's what it looks like. I somehow suspect my fall 19 actually looks the same. No, it's different. So my fall 19 is different from, so how about my spring 20 then? One of them is the same. No, it's different, all different. Okay. Then you have 2 previous tests that you can study from that I already went over. Yeah, and then 2 new tests that I never go over in class. Okay, so this weekend, make yourself busy with doing well with my old tests. If you have any question, you can ask me next week. Because the week after that is your test. Okay, the week after that is your test. Now, test 1 is the easiest test among all 4 tests. But simply because it is easiest, it doesn't mean you don't need to study. In fact, that's the easiest one. Make sure you do very, very well on that. Are you with me? Everybody okay with this?
Yes.
Okay. It's to the point that I want you to promise me get that 90. You know? Okay, please get that 90. Okay. Even an average student, like you don't need to be smart to get that 90 points in my class for that test 1. Your test 2 later on will be so difficult. I mean, I'm not making it difficult, but from my experience, test 2 usually the most difficult one, test 2 and test 3, such that first, even if you get 50 in my second test, I will be okay. It's like, if you get 50 in my second test, I will not tell you to drop the class. If you get 50 in my first test, deep in my heart, it's like, what do you want? Like, why don't you just drop the class? If that happens for your test 1. For your test 2, if you get 50, yeah, I mean, okay, less than 50 is bad. Okay, if you get 55, I still see people getting 55 in my second test end up passing the class. That's what I'm saying. But nobody getting 55 in the first test end up passing the class. No. Okay, so try to get more points right now instead of waiting until the next test and try to study harder. No. Okay, this is the easiest test. Please do well. Okay, please promise me that one. Please promise me this one, that one. You already spend your time with me coming to class, especially, right? And of course, other people will listen to this lecture. But what's the point of you working hard, studying hard, but you don't study right? You still need to study right from the correct resource. Okay, the first two sample tests I post here, we already went over that in class. Okay, the last two, I went over part of that in class. Okay, that's for today. See you then on Monday next week.